Hello. In this lecture, we want to try and implement the Blindfang lighting model with WebGL. The projects related to this lecture are the Shaded Cube, Shaded Sphere 1, and Shaded Sphere 2. We are now prepared for performing lighting calculations with WebGL. We will look at functions in mv.js that come to our help for implementing the lighting model and making lighting calculations. In this lecture, we only look at flat surfaces and we will do shading in the application just to prove the concept. In the next lecture, we'll talk about carrying out the lighting calculations in the shader, doing them in the vertex shader or doing them in the fragment shader. In order to perform lighting and shading calculations, we need to know about the light source, material properties, the surface orientation, which determines the normals, and the viewer. Many shading functions in the fixed pipeline desktop OpenGL have been deprecated. And that actually works to our advantage. We are not limited to the application anymore. We can do shading in shaders. If we normalize earlier, calculations become simpler. For example, dot product will achieve the cosine of the angle between two vectors if the vectors are normalized. Remember that rotation and translation do not change the length, but scaling does change the length. So after the scaling transformation, we need to normalize again. There is a normalization function in GLSL and there is one in the mv.js library. If we want to normalize a vector in the application, we use those. Here, we are showing the derivation of a normal for a triangle. We are picking two vectors on this triangle. For example, this vector and this vector. We find the cross product of these two vectors, and that will give us the normal vector, and then we divide the normal by its size, and that would be the normalized normal vector. Note that the right-hand rule applies, and here it determines that this triangle is outward facing. We sweep from this vector to this vector, and our right thumb is going to show the up direction. For each light source, we can set an RGBA for its diffuse, specular, and ambient components, and an XYZW for its position, as it's shown here. This is the position, and the first three are for the diffuse, ambient, and specular components of the light. The fourth element is the opacity, which is almost always 1 in this course for our light sources. Again, the light source colors are specified in RGBA format. The light source position is specified in homogeneous coordinates, and the last component W is 1 if we are specifying a finite location, and it's 0 in case the source is a distant source at infinity and therefore the rays are parallel. The distance term is usually quadratic, like you see in here, where d is the distance between the point being rendered and the light source. As we discussed before, spotlights are just like standard point sources, except that they are directional. Their coverage is based on this angle theta. And if we want to make them realistic, we need to make the intensity a function of the angle, with maximum intensity being achieved at the center of the spotlight, and it gradually decreases and drops to 0 at theta and minus theta. Spotlights are easy to accomplish in WebGL. Ambient light depends on the color of light sources. For example, a red light in a white room will cause a red ambient term that disappears when the light is turned off. Also, we can have a global ambient term that's often helpful for testing to see if everything is okay. So it's very good for debugging purposes. Both of these are easy to accomplish in WebGL. Moving light sources is a very straightforward thing to do because a light source is a geometric object. It is like any other geometric object. The position and direction of the light source is affected by the model view matrix. We can have all possible combinations depending on where we place the direction of light in our code. So if things are being animated, meaning there is a time variable and we are re-rendering, we need to move the light source with the objects. Or we fix the object and we move the light source, or we fix the light source and we move the object. And finally, we can have both of them moving in different ways independently. So we have tremendous flexibility, and it's just a question of where we place things relative to setting or changing the model view matrix. The light source properties are straightforward. We need to specify the position of the light source, here 1, 1, 1, and the red, green, and blue components of the light source for ambient, diffuse, and specular parts. These parameters have actually been used in the Shaded Cube project. Here the specular and the diffuse components are the same. They are both 1, 1, 1, so they represent the color white. And for ambient, we put a little bit of gray color. We have 0.2, 0.2, and 0.2, and that represents a little grayish kind of light. So if we're gonna see any color in our objects, it's because the materials of the objects absorb differently from red, green, and blue. As we learned in the last lecture, material properties should match the terms in the light model. So they should match these three. The variables here represent ambient, diffuse, and specular reflectivities of the material, matching the ones that we specified in the previous slide. The ambient reflectivity here shows a small amount of purplish color. We have 1, 0, 1, and these are going to be multiplied by small numbers at the light, 0.2 and 0.2. Therefore, we're gonna have a small amount of red, small amount of blue, and that's going to give a little purplish color. And this purplish color is not gonna be dominant because these coefficients are very small. And we have defined a good amount of red and green for diffuse and specular reflectivities. Red is going to be reflected totally, and green is going to be mostly reflected and slightly absorbed, and blue is 0. This means blue is entirely absorbed. So given that the light color is white, we expect a yellowish color from both of these parts. As you see here, the color for the diffuse and specular is dominant. We expect a yellowish color, and we see a yellowish color in this Shaded Cube project. We always multiply components of light terms with corresponding material terms, as you see in here. We have seen the multiply function MULT before. Here we are giving it 2 vec4s. All of these have 4 components. And here we want to do the lighting calculations in the shader. So we need to send these information to the shader. We send them over as uniforms with the function uniform for FV that we have seen before. We are sending the ambient product, diffuse product, specular product, light position, and material shininess. Lighting calculation for this project is done in the vertex shader. What about normals? We will actually add the normals to the function quad. If you remember, the function quad organizes vertices into two triangles forming one face of the cube. We find the normal for each face by finding the cross product of two vectors on that face, and then we normalize it, and in addition to vertices that we push in an array, we push normals into an array, and eventually both of these two types will be placed on the GPU. The complete code can be found in the Shaded Cube project. The JavaScript application file has all of these, and the HTML file has the shaders. For regular objects like these, we can ignore the back face. However, in objects such as this sliced sphere or this open parallel pipette, the back faces may have different material properties, and we need to handle those in the shader. Material properties are specified as RGBA values. The A value can be used to make a surface translucent. For the time being, we mostly set alpha equal to 1, and we should not have any problems. Later, we will use alpha values smaller than 1, and we will be able to blend things together and see through them. Alpha is this A that I'm denoting in here. Doing shading calculations in the application is bad for obvious reasons. In the Shaded Cube project, normals are the same for each face, so it does not matter a lot where we calculate the normals. We can calculate them in the application, or we can calculate them in the shaders. Here we did it in the vertex shader, I believe. For the spheres though, it matters where we calculate the normals. Shaded sphere 1 does not look very good, and that's because the normals are calculated at the level of vertex in the vertex shader. In shaded sphere 2, on the other hand, normals differ for each point. This means we are doing the normal calculation in the fragment shader at the level of fragments, and that's why it looks better than this. In the next lecture, we will be making a formal comparison between doing lighting or shading calculation in the vertex shader and doing them in the fragment shader. Fragment shader is actually where we really want to be doing the lighting calculations, because the resulting objects will look more fine-grained if we do so. Remember that doing the shading calculations in the shaders will free up the CPU to do other things. So we almost never want to do the lighting shading calculations in the application. Here is just a reminder of the WebGL workflow. We start at the application, and the last stage of the pipeline is the frame buffer, which is displayed. In the next lecture, we will talk about carrying out the lighting calculations in the shaders, doing them in the vertex shader or doing them in the fragment shader. We'll go over two interpolation methods for performing these calculations.